Okay, this is the final half of the final lecture for the review Unit 1, and we're going to continue discussing the complex variable geometry and a couple of interesting physical phenomena that come with this, such as vortices, that are in this week's problem set, at least related to that. What I want to do is just review real quickly the basic ideas. It's on the third screen there that we talked about in the last lecture. Idea of inventing source-free vector fields in 2 dimensions and having fields that have no divergence and no curl. That's a field that has an orthogonal coordinate system with the force lines and the flux lines. And I'm going to look at a couple of those. But in particular, a lot of the time I want to spend on is one particular field function, the monopole, the one that has a force field given by 1 over z and a potential field given by log z. That's the integral of the force with respect to distance, complex distance. And it is the central character in complex analysis. And so almost all of the mathematics about complex variables tends to revolve around Cauchy's integral. And Cauchy's integral involves that particular 1 over z. So that's again. Now what I've got up here on this particular old-fashioned program, and TC is working on a new-fashioned program, which is not ready for prime time yet, but when it is, it will be a wonder to behold, since it will have a lot of 3D pictures available that make it easier to visualize these things. In any case, the thing that we were doing, and I'm going to start over here, the usual links are about the same in this lecture as they were in the last one. The basic idea here is, first of all, that we really treat z and conjugate z as independent variables that are on the same plane, you might say, with x and y. And the idea of taking a derivative with respect to either the z or the z star and writing it in a chain rule using the partial derivatives of x and y with respect to, say, z or z star, that you get a operator, a partial derivative with respect to x minus I times the partial derivative with respect to y, with this little 1/2 in there. So that the whole theory that we're putting here that makes physics and mathematics, I think, more palatable in the complex domain is based on the idea of having a field that is not a function of z, that is this f star, this, for example, the first one we did was just plain old f of z equals z, well, a constant times z, but we left that to be 1. And then we made a field out of the conjugate of that. So all we did was take z and conjugate it. That means put a minus in here. We would have also conjugated the a if it had been complex. That is part of the bargain here. But in any case, when you get done doing that, you fix something that is not a function of the independent variable z. That is, it has 0 z derivative. And we showed that the z derivative, that is the derivative with respect to z, has a real and imaginary part that is half of it, the divergence. That's this combination right here, the 2-dimensional divergence And then this combination is one component of the two-dimensional curl. So the flux differential or derivative and the rotational or curling circulation derivatives are isolated as real and imaginary parts of the derivative. And we're working with a two-dimensional field which will have those properties. Now the one we're about to talk about mostly is not just plain old Z that we started and showed the basic mechanics of this little schema of looking for functions that are not a function of Z and seeing their properties. That is true also of the one that's on the screen right now, which is the function 1 over Z. And this particular function has very simple coordinates associated with it. The f of Z equals Z had the hyperbolas that result from a quadrupole force at a great distance. And we'll talk about that soon enough. But here the equipotentials are not hyperbolas, they're circles. And we have taken already in this class the polar coordinate system as our way of learning about the thing that we really need for the rest of the course. And that is the mechanics, or I should say the mathematics, of generalized curvilinear coordinates. This is definitely a curvilinear coordinate system that's being built here out of the equipotential lines. And if I go here and ask to see the vector lines as well, the flux vector potential here, and redraw it, it remembers what I've done there. And then these are the radial lines of the function 1 over Z field, the streamlines that come there. And they're always in the direction of any of the force lines, force vectors that you see there, which are drawn with their lengths proportional to whatever the actual force value is. That was a bad one right there. I'm trying to get this thing as symmetric as possible. Because, like, again, to look at the three-dimensional view of this from 2 points of view, I'd like to look at the three-dimensional picture that shows the scalar potential being plotted, but also the vector potential being plotted. It's very different in this case. Okay, so that right there is the map of the field. Now you might say, hey, is this thing really divergence free? I see a lot of things diverging here. If I were to draw a flux boundary right here, gosh, I think maybe there's some divergence. These things are getting smaller as we come out here, but it is in direction, they're certainly diverging. Well, what's true is if I draw a flux boundary right here, the test is that as much flux cross going into that boundary as came out of it. If that's true, then there's zero divergence. And the mathematics is telling us this is zero divergence. So wherever I put a boundary here, wherever I put that boundary, really a lot of flux is going in the back door here, but the back door is shorter here than it is here where the lesser vectors are coming out. So in the long run, you have to believe the mathematics that really divergence is zero everywhere. Well, not quite everywhere. There's one point right at the center where all the divergence is. And that we didn't have with the other one. The other one, all those points where the sources were at infinity. Here, they're right in the middle of the picture. Okay? So that's I think, an important thing. Now, it's pretty obvious that there's no circulation in this one, but in a little bit here I'm going to show you, and it's on the screen down there, the vortex, the elementary vortex function, which is I over Z. this is 1 over z. Okay, so those two are taken care of with just a really simple algebra, and we need to explore both of them before we go too far with this into this lecture. But in any case, this was what we worked with when we took f of z equal to z, and then conjugated it. That's what you get. At the very end of the lecture, I'll talk about where we do non-analytic functions and get something out of that. We may get to that, but that's sort of a favored hobby of mine that I haven't been exploring recently. In any case, this is a picture of the streamlines, vector potential lines, and the equipotentials for the f of z equals z. And that has a nice shape to it. Now let's see if there's anything else. I'm going to remind you the main thing that we need to learn to go on in this course is how to manipulate and use GCC coordinate systems that are more complicated than the polar coordinate system that comes here, for example. This one is just a bit more complicated, and I've given you a couple of examples for problems in next week that are due next week. And those probably will be due Wednesday. They're not that hard. They're very simple problems. So after you get done with Friday, get to work on those. Okay, let's see if I have anything else I need to say here. And that, I guess, is the important thing, is that you can write this, the derivative or write this force field as a derivative of a potential, and that potential was obtained by taking an integral, just a straightaway integral of the f of z equals z. And the integral of z is z squared over 2, because you have a half. But the idea is that that's z squared, that's x plus iy squared, so I get this part for the scalar potential, and then the vector potential is the xy part of it. So the vector potential lines, that's xy equal a constant, are the equilateral hyperbolas that you see with these blue lines. And the x squared minus y squared is another kind of hyperbola. Those are the red lines there that are equipotential and represent topography lines for the scalar potential plot. But these guys are topography lines too for another plot. That's the plot of the vector potential. Well, okay. And they're kind of similar, and you can see they're similar in the sense that it doesn't matter at this point whether you write the force in terms of scalar potential and just take the 1/2 away completely and forget about the vector potential. So that's a perfectly good description of the force field here. And the forces would all be vectors perpendicular to that. But then you can also just forget about the scalar part and just take the put a 2 on this one, and you've got the whole story as far as the actual vector force here. It's the same in both of these cases, though it looks like we're dealing with very different construction to get that force. The answer always has to be the same. And the answer is the same because of symmetry relations, so Riemann-Cauchy. Okay, is this making sense? I mean, I want to make sure that this is really understood, because we're going to be playing with it in a couple of different ways. Okay, I'm going to start here, going ahead. Now, here was just to mention the Riemann-Cauchy and something else. We could do this completely anti if you wanted to, but we'll stick with this particular approach that we have here. Okay, and also I mentioned it's not analytic if it's got a z and a z star. It's got to have one, then say z, then it's analytic in z. Or it's got to be all z star, and then it's analytic in z star. You can have those two worlds if you want. And we are sort of working with the Z-star world in everything we do. Okay, and then there's the whole business of flux integrals, which I was just sketching out there for you. When you go through this manipulation right here, and I'm going to go ahead and run this guy down here ahead a little bit so that we can talk about this fairly clearly, and that's where I'll stop that. And this is it. But this part right here, where I ask you, what good is a potential? Well, potential is something that gives you an integral of a force field with just arithmetic. In other words, if you know the scalar potential, and if you're working with just the scalar potential without the 1/2, you could forget about that guy right there. But at this point, it doesn't make sense to do that because these are really very physically different things. The real and imaginary part of a change in potential is going to be different numbers. One of them, that's this one, is calculating for you the circulation integral, that is the work integral, the integral of force dot distance, the most elementary thing that we've so far talked about in mechanics. And the idea is you're making a sum of the projections of those green vectors on the actual curve, and if it's a loop, then you do it all the way around to see if you get any work by going around a loop. And for this particular field, you don't. That comes out to be 0. But in any case, that's what it is. That's the real part of the complex integral. Then the imaginary part is just sort of the flip of that. It's the integral of the force dot with a normal to some curve that you are interested in, some path that you're interested in. And that's the flux integral, the projection of the force vectors across the path, dr, you see. So this is all stuff that is worth getting an intrinsic feeling for if you're going to be working with mechanics in fields. This little two-dimensional story we're telling here really makes things very simple. Okay, now the plot of that f of z equals z, the z plot, is a saddle, and you can see when we were looking at the hyperbolas that those hyperbolas definitely are topography lines for this saddle. But these flux lines that come talking down here perpendicular to the fall, perpendicular to the topography lines, what you might call, if you're a skier, the fall line, okay, the thing that points downhill. Here they actually point uphill because we're doing mathematicians' forces, but in any case, there's no arrows here, so I don't have to really talk about that. But in any case, they're both hyperbolas, and the red ones are more obvious ones that deal with scalar potential. But the vector potential is there too. It has to be to make it a complete story. So that's a three-dimensional picture. And by the way, if you were looking with your computer or the text, all of the pictures that have two frames in them are walleye. That is, you put your nose right between them and sort of get back. You'll get a three-dimensional drawing, and some of these things that we're going to do are pretty complicated. You really need a three-dimensional drawing to see some of their features. But we'll get to that soon enough anyway. And the other thing I want to make sure in this review, and it's this guy I've got to go ahead on, I want to make sure that you're in the next problem set ready to see the Jacobian again and make use of it and see the covariant and the contravariant vectors for these more complicated coordinate systems. They're still orthogonal coordinate systems. They still have a metric tensor that is diagonal. Not only is it diagonal, it's a multiple of the unit matrix. That's one of the properties of these complex coordinate systems that we're making when we use complex variables to build all of this stuff out of field lines. That's what you get. You get a real, very simple OCC. And OCC that has a diagonal metric tensor. In this case, it's just r squared. So the Jacobian involving the partial derivatives with respect to the potentials, scalar and vector, give you the covariant vectors. But over here, when you look at this, the flip of that, that's these guys right here, the rows. Here you're getting the contravariant vectors. There isn't that much difference between them. This is x minus y. That one is too. That's one of the features of using an analytic function. That symmetry will be preserved. But that is just one part of the story. The main thing is that it is the Riemann-Cauchy relations that make us have an orthogonal coordinate system, but they have even more symmetry than that. They do give us this, a unit metric, just like the Cartesian metric. Okay, anything else here? Oh, and this is going to come up too. If you go ahead and look at the divergence of this, that's definitely 0, but that divergence can be written as a second derivative of the scalar potential, also of the vector potential. This works too. But this is when we say that these force vectors, but also the potentials satisfy the Laplace equation. The Laplacian operator is a double second derivative of both the independent variables x and y, sum. So what that means is the curvature, if you have some curvature this way in a neighborhood, you've got to have opposite curvature at every point the other way. The curvatures have to cancel. That's kind of weird, right? And what you're doing is you're making a minimal surface. So these surfaces that we're going to be plotting here are minimal surfaces, such as you would get if you had a really sturdy soap film. You can get this soap film that doesn't pop very easily, and you had a plane and you just poke up in it, you're going to get this thing. And everything on there will have 0 total curvature. I mean, that's another part of the symmetry associated with being analytic, an analytic function, satisfying Riemann-Cauchy. Okay, so there's a lot of neat physics besides just fields here. You want to play with temperature gradients and flow of heat. This is the thing to look at. That's what this is good for. Lots of things.
Isn't there any curvature at any certain point perpendicular to the
say that again.
Isn't there any curvature vector perpendicular to the surface of thing right at any point?
Definitely in this thing. Let's go back to this picture, okay? And I say I measure the curvature going along projection of the x-axis. I see a very positive curvature there. But at any point, I've got to see the opposite sign curvature, namely pointing down. As I look at the x-axis first, and then say the y-axis is going that way, I would see, and you can see that saddle's that way. It's down this way, but it's up this way.
I can't imagine it, because when something is like a saddle, eventually it has a curve. It has a curvature in some direction, an overall curvature.
Well, every point, you're only looking at points with your second derivative, right? Okay, so you're looking at say, let's just go right to the center of it, right? And I see a second derivative here in the x direction. It is really definitely positive, okay? But then I just turn my hand, okay? And there will be an asymptote there where the curvature goes to 0. And then, as I turn my hand into the screen, I see it have to cup it this way in order to keep my hand on the saddle. and that's a negative curvature. And they're both at this point. I'm measuring at a particular center point. Very obviously, the curvatures are canceling perfectly. I have just as much curvature up this way as I have down going in and out of the screen. And that's a three-dimensional drawing, right? You see that clear. That's maybe a little hard to visualize. That's why I do it in 3D to show it. And you look at all of those 3D drawings for every one of the things we're going to do today, and you'll see that every point, yeah, curvatures cancel. So an analytic function can't have a dome, because that would be two negative curvatures. It can't have a cup. That's two positive curvatures. You see. So that's why analytic functions have to go to infinity at some point. They have to have a singularity of infinity at some point. I mean, that's a famous theorem that is quoted without very many people understanding it. Does that answer your question?
Yes, but I'm still confused. I can't imagine it.
Okay, well that thing, how many people have the same problem? Just out of curiosity, visualizing. You've got that wonderful program. You're going to send me a thing that will do 3 dimensions and things. Do you feel comfortable understanding curvature? I mean, you know, second derivative is the curve, and it can be 0 by being flat. It can be negative by turning down, or it can be positive by going up. And the saddle has both up and down, and there's a region right up there. You see the topography lines are real close together, so there's no curvature along that line, up or down, but the sum has got to be 0 there too. They're just both 0 there. But wherever it starts to get a little bit positive, like there, there's a curvature that's countering that negatively. Every point is this way. It's really hard to see when you get down where the thing is steep, but still there. I mean, that's an interesting little piece of topography, or whatever you want to call it, about this mathematical business. Bill, are you making sense out of this?
Is the same going to be true for that one?
Yes. And that's bizarre, because when we plot this one, and I might as well do it right now just to get it, we'll plot the scalar potential of this sucker, I hope, by just pushing this button right here. And there we are. Okay? Then you say, my God, that thing looks like it's got positive curvature, or what? But it doesn't. It's got kind of positive or negative curvature there, but then this is positive, going this way. So every point on this things go crazy right at the center, remember? So that's off. But everywhere else it's satisfying Laplace's equation. Second derivative with respect to x plus second derivative with respect to y, 0. It's all you can get. I mean, maybe that's a better one to look at. A flower, right? It's got this very positive curvature here, but it's got negative curvature there. Does that help? I mean, this is, you know, for a lot of people, this takes some effort to, you know, get yourself so you're imagining you're climbing you know, doing some hiking or something. You can hike around the equipotential lines there, and
work.
you know, as long as you don't slip and go down this hole here, right? That's the real way to get used to these mathematical functions. Imagine you're there. Okay, what do you see? You know, what do you feel? And you're going to feel some pretty high derivatives right here, but if you get back into this region here, you probably don't need technical climbing equipment anymore. But you still have a slight curvature right there, but then I have a slight negative curvature there. There's positive there, canceling negative there. Every point is doing that. That's what's magic about these functions.
The way you explained, you said like you don't need any climbing equipment. Should we need any at every point? Because you said like,
Well, it depends on your coefficient of friction. I don't think I could stand there, but I could probably stand there
But the total curvature
without
is,
sliding.
so the total curvature is 0.
The changes in potential is thought of as vertical.
It does help, maybe.
The red lines are equipotential lines
Yeah.
that takes a little effort to hop, and those are vertical changes, whether
Yeah.
positive or
You
negative.
see,
There it
when
is.
you look this way at the thing, and let's zoom in a little
Red
bit
will be your
here,
potential.
so you can see it. Okay, we're right in this neighborhood, it's like the x-axis, y-axis, you'll see that all of the red lines are at the same height. That's what's called a topography line in maps, right? When you get a geodetic map, you know, they'll show you lines. And when those lines get close together, that means big slope, right? Big gradient. You're going down a cliff. Okay. Well, what they don't put in there is a measure of the curvature. Curvature is, you know, a second order effect. Right, so it's a little hard to get used to that. And you can see very much curve right there, but every one of the curves there have the red, I mean, the other perpendicular to that is up. That's positive curvature in the y direction, but it's negative curvature down in the x. Does that help at all? And this is a good function to play with, to do that. Because its vector cousin, its vector, which we'll show in a minute here, is very different. Very different. But still, it's got to have zero total curvature. Double derivative with respect to x plus double derivative with respect to y, absolutely zero, unless you're sitting on a singularity, right? At minus infinity. Okay. Then all of that stuff accumulates there, so to speak. That's being a little risque. Okay. Does that help? I mean, it's
It does, but
it's going to
I
take.
still feel like when two curvature components cancel each other in specific directions.
Two directions.
Two directions. In
Yeah.
one direction, there are kind of constructive. That's why we have a curvature toward right for that guy, and
Well,
it's not this way.
best way to describe curvature is not so much slope, it's the change in slope, right?
It's the cuppedness.
In other words, we're
Concave
taking
up,
a derivative
concave
of
down.
something that measures slope. Okay, that's when you get curvature. So you start with some function, you pick a point, and you see how much slope it has. First in the x direction, then in the y direction, right? I mean that then tells you where the gradient, what the gradient is, right? The sum of the partial with respect to x plus the partial derivative with respect to y, summed up. Now, you're asking a different question with the second derivative. You're asking, how does the slope change? Does it go from negative to positive? That would call positive curvature as I move in that direction. And then this thing is telling you, okay, if you found positive curvature in the x direction, then in the y direction you find equal amounts of negative. In other words, magnitude the same, but it cancels. And then you know you're in a region where there's no charge density, if this is electricity we're talking about. Does that make sense? I mean, that's what the Laplacian equation is telling you, if it's zero. If it isn't zero, if it's some function of x and y, let's go Poisson's equation, and that's something that it's equal to is the charge density, right? Remember that? I mean, that's your electromagnetism first equations, right? Is that making sense? Because yeah, this is a heck of a good way to get your mind around a lot of things that you're going to have to deal with in physics. And forces, their derivatives are really important. Okay? Thank you for the question. I mean, this is stuff that has to be brought out in the open, and then you have to wrestle with it. Yeah, it's a real mind game, but it's a fun mind game. And we're making it easier with some, virtual reality things and stuff like that. But when you put those things all aside, it's got to be in your head, and you can't rely on those crutches all the time. Okay. As I said, that is Laplace's equation right there. Now, let's get this one, the morning glory here, down in the best way I can. Show both the real and imaginary. This is just the thing that involves the scalar potential. The vector potential's got more to it. In any case, 1 over z is the monster function for complex variables. It's the one that drives everything in all of the mathematics. You got to worry about this more than any of the others. All of the other powers, yeah, they're easy to understand. This one's the one that just drives you nuts. Now, if we take a force F equal 1 over z, that's what we've got right here. A is just plain old 1.0. That would be what I would call a source monopole. Most people would call it that. But when I integrate that sucker, I get a logarithm. Okay, logarithm of z. That's what I'm going to be seeing as the real and imaginary parts are going to come out of that logarithm. And I'm looking at the logarithm of a x plus I y, which is kind of weird, okay? But we got to deal with it. A logarithm of a product is the sum of the logarithms of separates, and the logarithm e to the I theta is just plain I theta, okay? And we're dealing with that here. We're dealing with z being r e to the I theta, and so that's what we're taking an integral. I'm sorry. Yes, we are taking the phi here as an integral of the force 1 over z. Okay, and we're getting a thing that looks like what I showed before when we looked down into the hole here. There's a hole here that you would get by being on top and looking down into this. So this is a view into the thing here. Now, the whole idea of this coming apart here, that is, what I'm doing is I'm taking this logarithm of a product here, so I end up with two logarithms. The logarithm of r, the first factor here, okay? And then the logarithm of e to the I theta, well, that's nothing but I theta, so I end up here with just I times theta. And this one's the logarithm of r. So those are the two pieces. And this one is the one that's giving the vector potential. And that corresponds to all of these lines going around here. And then this right here is the actual logarithm. So what you're seeing plotted right here is the curve of the logarithm, which we've had lots of time with the problems to play with. But on top of that curve, that curve whose slope is going from a high positive value to less positive, so that corresponds to what I would call reduction in slope, and I would call this the negative curvature. On top of that is some positive curvature. If I go here, the slope is going to go up as I go across that region right there. I'm just emphasizing once again that sum of those is 0. And we're taking them separately here. The radius is out, and then the angle is across, so that's a good thing to do. These things are a function of theta only. They're just plain old straight lines in some theta direction, and then the R is constant R, constant radius. All of them are circles if you look down from the top. Okay, does that make sense?
Do you do scalar sum for the curvature over there?
That's
Is that a scalar sum for the curvature over there that gives the 0?
The 0 is gotten by taking the partial derivative with respect to coordinate x or coordinate y of this whole function. That is, this phi that we've got here is a logarithm of the that's it right there, the logarithm of z, right? That's the function we're looking at. We've taken it apart into real and imaginary parts here, and then those two parts correspond to either circles, r is a constant, okay, or angle, theta. Is that helping? I mean, this blue thing right here corresponds to a particular theta. So that are the polar coordinate representation of this function. Is that?
Now, we have another view coming up right after this.
Yes. And that's where we plot this guy. That's in just a minute.
Bringing them two together should help.
Yeah.
After that, it should jump.
Let me see if I can go ahead. I guess I don't have a picture of this thing sitting by itself as a 3D view right in. I do here. And
here's your theta.
That's what we want to look at. Let's go ahead and do that right now. I want to plot A versus all of the coordinates. A vector potential A I want to plot, okay? So without changing anything, I'm going to leave all the lines I've scribbled on there. And instead of plotting the scalar potential, I'm going to look at the vector potential.
Of which we have one dimension.
That's weird. What in the heck is going on there? Well, we've got the thing all turned up on us. I need to sort of bring it back a little bit and maybe turn it a little bit so you can see this thing is really cool, and we need to look at it as carefully as we can to see what it's doing. It's really quite amazing. See if I can get this thing turned around.
A couple branches.
Yeah, it's not a trivial thing at all. Maybe it would help if we tipped it up a little better here. I think that might show it. Certainly the right-hand side of that picture is showing what I want to show, but there is the rest of it that we need to look at. And maybe I'll zoom out just a tad here so that we get a better idea. And then I think this will help here to look at this crazy thing. Because you see, it has to cut off. This thing is basically that. But what do you see there? But those theta lines, constant theta lines, the polar angle lines, are all straight out from the axis. This is a spiral staircase. You know how many of you visit a tall lighthouse, and they have a stairway inside there that's a helicoid. This is the helicoid, half of a DNA molecule. DNA molecule has a spine right in the center, and then it's got a stairway around that climbs up, a circular staircase. Half of it
I've just got half of it here, okay? They go, each one of these blue lines is coming out at equally spaced intervals and going into the screen. This one you really could use some 3D to see it, and that's why you should look at the either your lecture notes or the textbook where the 2D drawing is in place. It is in place right here. That's probably a good view of it. That doesn't even need the 3D, but you should get your nose down right there and let your eyes just sort of swim. So the right eye's looking at the right image and the left is looking at the left. And you got to learn to do this because you're going to be working with weird solids and molecules and all kinds of stuff, and they are printed in stereo when it's difficult to see their structure. So it is a good practice to be able to do without the glasses. We have lots of glasses here for doing it if you just can't get your eyes decoupled. But there is the staircase right there. That's what it's telling you. It's telling you that the imaginary part of this thing, the vector potential, is climbing up, and it's only a function of theta, but as you keep going, finally you climb up 2 pi. You go around the staircase, and now you're 2 pi higher than you were when you started walking up those stairs. Does that make sense? Is that something that you can...
What are the red lines?
And the red lines, they're now looking like, I used to say that those are the blood lines. The blood is flowing down the staircase.
Yeah, but there is
And
also
those lines used to be constant phi lines, and they still are, but they're now doing the spiraling.
And then there is also one that is dropping straight down
It's a
Well,
pole.
also. So
Here, the program, plots the graph until it gets here, and then it just starts over again.
okay.
You see, this should just keep on
It's a single branch.
going, right, as a helicoid forever, right, and gaining 2 pi in altitude every time once around. Yeah.
So is that similar to this Mobius ribbon you have in here? Like wherever you start in a certain direction, you'll get the same thing after one turn.
You'll be in the same x and y coordinates
With
here
the phase
as you
shift.
are here. Yeah, and that's true every point, right? This is just showing going in one revolution. TC is working on making better programs that would just show this thing going up and coming from below, spiraling upward, linearly with theta. Linearly with theta. Yeah, that's the vector potential plotted in terms of all the coordinates we've got. It's just a bunch of straight lines
You never end up on the other
climbing
side
up
of
the
surface
staircase.
on this one. That one you do.
Is that-
Different topology.
Everyone see?
So are these the red lines the same as those equipotential lines?
We now have flow lines.
Which potential though? Vector potential right now is being shown. And so that's constant A, and then a little higher A, and a little higher A. A just is a function of theta. It is equal to theta.
Sure.
It doesn't care what the value of R is,
Pure magnetic potential.
right? So therefore, R's doing its thing. It's making a spiral around there, but the its height is determined by the logarithm. So as I vary theta, I go up linearly, but if I vary R in and out, depends on what theta I have. Where am I with regard to the height here? So here height is the vector A being shown, vector potential. Okay, is this? I mean, this sort of thing makes people quit mathematics.
Or go into it.
But if you catch it, wow, that's beautiful. You want to see the beauty of this, right? That's the important part of all of this stuff that we do, I think.
So let's say you are on that, no, not the imaginary one, the other one, and you're turning at the same phi.
Maybe the best way I could do it was to, this would be a typical theta line. Let's say that's theta equals 0, okay? So I have 0 height. But the next theta is going to be a little higher. And the next theta after that is going to be a little
Linear
higher.
with that.
So these are the blue lines doing their thing. You see, I'm just
But yeah,
showing you.
that I understand about the theta, but phi, that
The
phi-
angle.
the phi, the other
Oh, this guy. This
yeah,
guy.
that guy. Like if you're turning around
Yeah.
with the same phi, there is nothing, right? But in the imaginary part, they're like going below.
That's
the
right.
eye.
We're plotting. Oh, I don't want to pull this whole thing down here. We're just plotting this guy now. Before we were plotting this one, and that gave you the beautiful logarithmic term, right?
But yeah, I mean, I want to like combine them to understand what's going on.
It's really hard. These are both the same object,
Yeah.
but looked at from different points of view. Here we're concentrating on the variation that you get due to change of theta. That is due to the change of the vector potential. Okay, so in this case, we're looking at the thing plotted versus that. The R is just along for the ride. This part is just along for the ride. It's just going to be coming up, and there's no mention here of R, except the fact that as I go out, certainly it was true with this one, okay, here as I go out, the equal potential, this scalar levels off, makes this beautiful flower, all right, so there's lots of curvature on that surface. This one's weird, okay, because the curvature is associated with the red lines, that's the equipotentials, is that of a helicoid, or just plain helix. That's probably the best name for it. Does that answer anything? I mean, that,
It's like,
as
sort
I
of like
say, the
two
best,
different views. You start off with a red scalar potential centric point of view, and you get the middle pictures. And then separately, independently, you have the complex term, which we call the vector potential. That gives us another set of these two bottom pictures.
yeah, these two right here, these are the same, it's supposed to be 3D picture, so that's why you put your face here, actually see this very clearly.
And if you think of E and M, or in terms of E and M, it gels.
Yeah.
Because that's what we got modeled here. We've only got one dimension of the vector potential, though. That's one thing we need to point out. We only have one perpendicular direction.
And we have real discontinuity on this line. And we had it here too, on this line.
Yeah, just trying
The
to
vertical
figure out,
line that
like,
goes through the
ball,
center.
ball moving out like this.
Yes,
In
yes,
the 5 spot.
this one doing that.
Yeah, but that one ball, right? But in the 5 spot, what's going to happen is that ball will just go like this, right?
Sure. Or down, right or
Or down. But the ball will go like this in the other way.
The
perpendicular.
this thing right here, for any angle, is absolutely straight. In other words, that line just goes forever straight. But at another angle, it's a little higher and goes forever that way, absolutely straight. Okay, and so forth. And that makes a helicoid. That surface has a mathematical name. It's the helicoid. It's a single helix. It's what you get when you open a DNA and take one of the strands away. So the DNA can then make new DNA, right? I mean, that's what's going on in your body every minute of the day. That those helixes are being opened up and then closed again. It gives you the creeps, doesn't it? I mean, look how things are working. Yeah. The double helix would be if I had another line here and I went up with that, right? That's not what we're showing. We need a single here. Yeah. Is that okay? Just making some sense. Yeah. Okay. Let me see if there's anything I can do here that would make that a little clearer. One of the ways I can do this, and this is kind of screwy, is take a look at what the plot would be if I had a vortex. Or if I was dealing with a magnetic field around a single wire. Okay, this is Magneto Statics, which you usually don't study, but anybody that's working with, headphones and microphones and things like that, that's a very important thing. But here, I have I times z, actually minus I times z. That's the same deal here. It's just that the roles of these two components are going to be reversed. I'm going to go ahead and just shout of this, as I'm going to go ahead here and pick a dipole there, erase the changes, and then I'm going to come back and redo this thing with the constant multiplying it to be I. Right now I have the constant A equal 1, and the imaginary part be 0. But what I'd like to do is bring this right here to 0, and bring this one to 1. Okay, I'll make it close to 1. Let's just let it be 1. Okay? And so let's see what this looks like when we plot. First of all, I'm going to do the field. Okay? You can see that all the force arrows are making a true vortex. Now you might say, oh boy, those things really are curling everywhere. There's curl everywhere. No, there isn't. I draw another boundary here and do my integral of f dot dr. I'm going to get a real big value on one side, but there's going to be more going the lesser drawing here that's backwards on the other side. So the circulation everywhere here, the curl everywhere here is 0. It's all piled up in the center. And that's where the source of the curl is. Okay, but in any case, I go here and plot the streamlines for this one. The vector potential for this one are now the circles. Okay, so that is just the opposite of what we just got done doing here. This vortex is the same sort of mathematics, just with a couple of sign changes makes a big difference. Like everywhere I draw something that's a circle, and I'm just sort of spacing them out here so that we can see it easily on the drawing. Maybe this one will be an easier helix to look at when we go and look at this scalar potential, the phi. Okay, that ought to be enough there. And then I'm going to go back there, and I'm going to get my scalar potential, and I'm going to plot it on this thing. And that is going to be a bunch of straight lines, but now it's straight red lines. So this is a very different thing as far as a magnetic field. The magnetic field lines would be along the blue lines for this particular device or structure. This monopole is key to so much of the mathematical physics of field theory and complex variables in general. So this is just the same thing we've been looking at with the colors reversed. Okay? And let's go ahead and have a look at it. First, I'll plot the scalar lines. In other words, I'll plot A as a function of coordinates. Same thing we had before, except now the red lines, you see, are the ones that are straight. Okay? The red lines are the things that are rotating around, making that. And that's what I'm trying to show right here. See, the red lines are the staircase up the thing, and it happens to be going this way. It's left-handed, but that can easily be changed by putting a plus sign instead of a minus sign on that. Meanwhile, the vector potentials now making the circles that are the topography lines for the flower. The flower's got blood flowing into or out of it. That's what the red lines are. The flow lines look like flow lines. But this is a vortex, a completely different piece of physics than this. But the same basic geometry. If you're colorblind, you couldn't tell these apart.
Looking from the top.
Yeah, looking from the top and not reading the symbols. Now the phi is the one that makes the thing that goes straight lines spiraling upward, and the blue flow is from the vector potential. That is from the B field. The B field is there if you're thinking magnetism. But this is a very good piece of mechanics, and I'm asking you to take a look at that in the problems that I handed out today. I think we have enough time to show some movies. We have to hear from the physics girl. She's done a beautiful job of showing vortices in the swimming pool. So we'll get to that in just a minute. But the vortices that we're talking about are vortices that have zero curl around them. That's very strange. Now remember, also, every one of these figures could be made with soap film. That is, if I could get a ring with a soap film, but have the soap film go around and attach here and attach there, then be able to say hold this one constant and take this stick and raise it up, rotate it. I would make a helicoid out of soap. No, I'd have to be a little careful. I'd have to have something to hold the ends. I'd have to make it finite. I can't go to infinity in all directions. But basically, if you just take a soap film and twist it, just twist a rectangular soap film, you get a section of a helicoid. And it's a minimal surface. That's the other thing these surfaces all are. There are no bulges. You can't have a bulge because then the Laplace equation isn't zero anymore. The Laplace equation is asking you, have you canceled your total curvature? If you haven't, you're not minimum energy yet. Okay. Now, where do we see vortices in real life. Well, go out at night with a really good telescope, you can get to see spiral galaxies. And this university, I mean, our astronomy department is a bunch of people really worried about spiral galaxies. In fact, Daniel Kafik thinks he has a pretty good theory of how they form, how they make it. It is not as simple as a hurricane. It's not as simple as a tornado. It's not as simple as this thing, which is just a bottle of colored water, 2 Pepsi cans, 2 Pepsi bottles. And what you do is you turn this thing over, and then you go put some curl in it, get it rotating. There, I think I got it. There you go. A vortex. Isn't that cool? And that's what I'm showing a picture of right here. It's just that thing. I took this this morning just to get it. So with that light, you can very clearly see this one. I should have photographed it using that light on it. There we go. It's starting to fall over. The bases are very strong. But that's making a certain curve, which I'm going to ask you to calculate what that curve is, just from thinking about what water does. We're going to see a better picture of a vortex, more complicated and more lively one in just a minute here. I think I can get it to come up on, and I'm going to go ahead and cancel this out and get back to this computer here, which I have already gone ahead and I'm going to zoom ahead here to the vortex section, and there are this one on the right, same as this, is going to show, I hope, a vortex. Now, if you put a complex number on top of 1 over z, that's when you start getting what we're talking about here. Something that has both divergence and curl. But everywhere outside here, in this particular thing, if it's in fact, there is none of either one. It looks like, boy, I got divergence, I got curl, I got everything. No, you don't, it's 0. And the surface that goes with that is really, it is spiraling helicoid. I mean, it is really, that one I am still not happy visualizing. Anyway, let's talk to Mrs. Physics Girl here. She's been doing this for quite a few years, and it's really worth, I hope I can get it up. I got it up this morning, but we're having trouble with the internet. You know, they're being very nasty about, they call YouTube a bad source. But let's see if I can get it going here. Yeah. Okay, I've got to skip the ad. Okay, yay, Physics Girl. There's what a vortex looks like from the top when it doesn't go down the drain. I want you to get that curve too.
I made a video recently on one of the simplest but most mesmerizing phenomena I've ever discovered. You drag a plate through the water, creating 2 dips on the surface, and sunlight shining through the dips will create 2 crisp black spots on the bottom of the pool that can persist across the length of the pool. But the dips in the water are just the tip of the iceberg, as they say. Underneath the surface is an entire half-ring vortex, aka a toroidal vortex. I had never seen these before, so there's so much more to explore. And I know not everyone else has a pool, so I took some of your awesome suggestions and I'm going to try them out. For this one, I have to get in the pool. I know it looks ridiculous, but this is not warm. You can see here as the food coloring is dropped into the dips. The best part, I think, are the reflections you get off of the surface. I couldn't see what I was filming, but this just looked way better than I could
Structure
have
there.
imagined, so we
Vortex
tried
around the
2 in
vortex.
sequence.
The red one cut the green one in half. The red one didn't die, but the green one kind of disintegrated. It was cool.
And of course it runs into my camera and dies.
The vortex hit on this end of the camera, and then you could see the death of the vortex just moving along the rest of the vortex. It almost looked like it was unraveling, which I'm hoping won't happen here. We're gonna put the pole in the pool and let the vortex pass by so that the pole cuts it right in the middle. And I'm hoping that it'll meet back on the other side, or it'll split into 2 vortices. Oh, it just kills it.
I think there's too much turbulence when there's an asymmetric collision of the vortex with an object in the water. Unlike when you hit a wall with the vortex, it's a lot more symmetric and it can keep that nice laminar flow in the spin of the vortex. I've been told that yellow is not the best color for a pool, so we're going to try blue and red to see how the fluid mixes.
Nice. That looks awesome.
It almost looks like the red is engulfing the blue. It's surprising that the colors don't mix together. It's almost like they stay in their own layers of the vortex. We tried a smaller plate just for fun.
Check that out.
I was a bit surprised by this one. I thought the ping pong ball would disturb the flow of the vortex, but it dropped right in and shows us how fast it's spinning, at least close to the center.
The motion of these vortices is really unpredictable. Like, sometimes they just seem to die for no reason. Sometimes they turn, sometimes they hit the wall, sometimes they spread out, sometimes they go faster. When it's spinning too fast, there's a lot more turbulence, and that breaks up the vortex. And if there are disturbances on the surface, that actually causes sort of that unraveling death of the vortex to move across it.
But I guess the unpredictability is what makes fluid dynamics so
Gimbal
fun
there.
and beautiful.
It's where the
Thanks for all
curl
of
is
the great ideas,
constant.
and thanks for watching.
So it's really good.
If you've enjoyed these videos and would like to see them continue, head over to www.physicsgirl.com.
Now, the rest of these I'll leave you to explore. This one is the University of Chicago that's made, I mean, he's made vortices that go and form knots. And it's really quite amazing about these. But the thing that is not shown on these pictures except a little bit here, that region right there, that's definitely what I would call negative curvature. If I call that positive, I call that negative. And what it has is a little boundary around a region that is rigid rotation. And rigid rotation corresponds to constant curl. So the curl around the vortex up to that point is 0. But when you cross a boundary where the thing finally, the viscosity takes over and the molecules get stuck to each other and form a rigid curve of some kind, I'm asking you to figure out what that curve is. So you're going to have 2 jobs. Figure out what the equation of that curve is, the curve that we saw in the bottle here, this curve. But also what happens if this thing had just died and made another curve right here. And the analogy is taken with the sophomore physics Earth. The sophomore physics Earth doesn't deal in curl, it deals in divergence. The divergence by Poisson's equation being proportional to the density of the mass giving the gravitational field. And there's no mass outside of the sophomore physics Earth, but there is constant density inside the sophomore physics Earth. So we ended up on the board a little bit, but also on your homework, a curve that comes in with the 1/r Coulomb potential and very nicely mates up with a parabola that makes the potential inside the Earth. There's an analogy. Is that analogy exact? That's what I want you to find out in that homework. Okay, so I have pictures of the extreme vortex. I want that first, but then we'll talk about the rigid rotation as giving us another curve entirely. Okay, so this is a lot of fun mechanics, and as I sort of suspected, and I'm thankful for questions to slow us down, we haven't got dipole yet. Let's take that up in the next class.
Excuse me, is it possible to extend this homework deadline?
Oh, say that again.
This one is the next Wednesday, right?
That's next Wednesday, yeah.
Would you mind to change it to next?
Make that one
Monday
Friday,
after
too.
that one. No, the Monday.
Um,
The Monday after.
Uh-huh.
It's
Isn't it?
over.
Good.
What is that?
Yeah.
Or
yeah,
after fog one?
yeah, I mean, we could just do a permanent translation in time if you want, and let you hand in on Friday every time. And then I would make the requirements, you've got to go to the colloquium. We're having a real problem with people not going to the colloquium. So, I mean, some of the colloquiums are terrible, I have to admit that.
Yeah.
But some of them are absolutely amazing, like the gravity one, right? If you
I
miss
made
that one,
that
you
one.
missed a big shot. That, unbelievable. And we're gonna have some more like that. But even the dumb ones, there's something in there for you to get, right? I mean, there's intelligence in there somewhere. The guy may not be able to display it, but it's in there. Yeah.
I may have to trim the back of that one up.
Yeah.